Hi, in this video, we want to take a quick look at clustering. So this is just going to be a first look at clustering, kind of a beginning introduction to it. And something I want to say, one of my former calculus students just gave me this mug. I'm really liking it. So I don't know if this is actually correct, that I'm the best teacher ever, but I'll go with it for now. One thing I really love about it is it's huge. It's a huge mug. It's the size of my head. Look at this. I can hide behind this. All right, that's good stuff. All right, so for clustering is unsupervised learning. All right, so first and foremost, what's the goal of clustering? The goal is to group our observations into subgroups, where each subgroup has like similar data points. So another question is, why would we do this, right? All right, so first and foremost, the first reason we want to do this is segmentation. We want to partition our data into similar data points and then use each group of data differently. Okay, so why would we want to do segmentation on our data? First and foremost, maybe we might feel that we want to build different models on different data sets on where we have like similar data points. Another one might be customer segmentation. So here I have a collection of data and on like customers, or maybe it could also be called market segmentation. And I want to break it up into different groups so that it'll be easier to target my marketing campaigns and my, how my customer relations type stuff to them better by understanding which group they're in. Also, we could use it for assigning caseload to employees that we have. So here the idea is that I have a whole bunch of customers and I need to assign a customer to a different employee. And I want the employees to kind of specialize in their group of people, their segment of the customer base. And so by doing this, I can mathematically identify what the subgroups are. Now, another reason why we would want to do clustering is that we want to do outlier and anomaly detection. So what will frequently happen is if I have an outlier or an anomaly, so when I say anomaly, that's like a multi-dimensional outlier. If I do clustering and I put points of similar data together, and it ends up that an observation is all by itself, it's probably an outlier or an anomaly. And so this is a way for me to spot, hey, this data point over here is not like the others. Another way is to use feature engineering. Now, this is one that if you look online, you'll see a lot of people try to use clustering as supervised learning, and what they're doing, they're really creating a one predictor variable feature engineering supervised learning model. So we can do better than that. So what I want to impress upon you right here, right now, is that clustering is unsupervised learning. We do not have a target variable in this situation. We are doing learning without a target variable. That's very important to keep that in mind. Now, I can use it for feature engineering, and it's very common when you look at like online blogs, and videos on clustering, people try to use clustering as supervised learning. Don't do it that way. It does not tune to a target variable. It does not tune to a target variable. I want to emphasize that. Now, another use of this is, let's say I believe I have different subpopulations in my data, but I don't exactly know what they are. I just see that, hey, there's different groups in here. Well, I could go through and I could use clustering to try and identify what those subgroups are. And then there's other inferences that we can base it off of, but this is probably the least important one. Usually for inference, like we probably know what's going on already, so like, I don't see a point. All right, now, so something I want to repeat, I already said this, clustering is not a supervised learning method. It does not tune to a target variable. It does not tune to a target variable. Clustering is only applied to our predictor variables. If I want to use clustering for predictions, you want to go and use k-nearest neighbor or proximoid centroid method. I've used proximal centroid quite a bit in my work. In fact, today, the models that I built were proximal centroid models. This is not a very powerful supervised learning technique, but this is a very simple one to explain to people who are not comfortable with mathematics. And so people mistake k-means for proximal centroid a lot. All right, so what are our methods for clustering? Well, there's three major ways. Now, there are a whole bunch of them. If you go into the R's clusters package, you'll see that there are tons and tons of different ways to do clustering. What I'm going to kind of just focus on these, and these are the big ones, is partition methods, hierarchical clustering, either agglomerative or divisive, and then model-based clustering. So a partition method is that we say, hey, I want to partition the data into 5 groups. The algorithm gives me 5 groups. Hierarchical clustering gives me a taxonomy. And agglomerative or divisive, agglomerative is where we take data points and we group them together until we form a complete taxonomy. Divisive is where we start with one big group and then we start dividing it into smaller groups to get a taxonomy that way. Honestly, in terms of machine learning, I don't see really an advantage of making a difference between these two. They're just different algorithms, but when it comes to output, I don't see one, like the distinction is not worth the time worrying about it. Now, model-based clustering, theoretically, we could use any distribution, but Gaussian distribution or T-based distribution is really the only ones I've ever seen like in application, and so virtually all of them are going to be Gaussian or T-based. All right, so let's do an example. Let's use k-means. So that is a partition method, and so what I'm going to do, I'm going to take some data. I'm going to partition the data into smaller groups. And then I'm just going to real casually take a look and see how good the groups look like. Okay, so I'm going to use the IRIS dataset. This is a famous dataset to work with. So I'm just going to go ahead and load it. Here's the head of the data. So here there are 3 different species. And the species is a factor in R. And then these columns are numeric variables. Okay, well, let's go ahead and let's just plot this to see what's going on. So if I use the pairs function and I plot the numeric variable, so you'll notice that I do not have species in here, but I have the other 4. I can look here, I can see like the red and green are together in the black, red and green are together in the black, red and green together, black, red and green together, then there's the black, red and green together, and so on. And we can see that there is kind of a separation between the red and the green, but it's not as distinct as black is away from the others. Okay, so, and then the numbering, so the species, the first one that alphabetically is Setosa, that's going to be the black points. And then the ones, the other 2 start with a V, and alphabetically, the second one is going to be red, the third one is going to be green. All right, so whenever we go through and we do clustering, if we're using a partition method or I'm using hierarchical clustering, I almost always want to center and scale my data so that we have mean 0 and standard deviation 1. Oh, that's a typo. Oh, I made a mistake. If we do not center and scale the data, columns with greater variance will have greater influence on the model. Now, that might be good, that might be bad, but if I don't want any particular column to have more influence than the others, I want to center and scale the data. There are some exceptions to this. Is like here we know better, like we have like a reason to not rescale it. Like we know that we want the standard deviation to be proportional to the influence in the model. If that's the case, then I don't want to rescale. If we're in the situation where the data range prevents a column from having much greater variance than the others. So in this situation, let's say I have data that's all that's all like on the range of 0 to 1. Well, if they're all on the same scale, I probably don't want to worry about rescaling the data. And then this last one is, in general, we don't want to rescale model-based clustering. And that's because of the correlations that model-based clustering, such as multivariate normal, will be able to detect. If I do the rescaling, that those relationships can get warped and distorted so that I can no longer detect them. All right, so now let's go ahead and rescale the data. So here I'm going through, I'm taking the iris data set, I'm taking the columns that I want, the numeric ones, I'm rescaling, so the scale function returns sample mean 0 and then sample standard deviation 1, and I'm making it as a data frame so I can use it later. If I don't do that, it'll be a different type of object in R. And so here, now let's go ahead and let's look at the mean. And you can see that using scientific notation, each column has mean 0 for all practical purposes. This is so small, I just call it 0. Now here, I'll go ahead and take the standard deviation of each of the 4 columns. And I can see the standard deviation is always 1. So each of these columns has equal influence in my clustering. If I don't want that to be the case, I can multiply a column by the amount of influence I want in it, and thereby changing the standard deviation, which changes the influence. All right, so now we can cluster the data with k-means. All right, I strongly recommend that you establish what the centers are when you do k-means. And so what I'm going to do, I want just to have 2 groups. And one thing that I like to do when I do my k-means clustering is I try to have centers that are very far apart from each other in higher dimensional space. And if I'm dealing with standard normal data, remember the 3 and -3 are the more extreme values that we can expect to see when I'm dealing with standard normal. And so what I'm doing, because I rescaled it, this is actually normalizing my data. Up here, when I did the scale, I normalized my data. Okay, well, I know that 3 is going to be a relatively extreme value if anywhere in the data, anything 3 or bigger is extreme. Anything less than -3 or less is going to be rather extreme. So what I'm trying to do, I'm trying to spread out the points as much as possible. Now I'm going to run the k-means algorithm. So the function is just k-means. I tell it the data matrix I want, and you notice I only have numeric columns in this data frame. And then I tell it the centers to start out with, and then boom, I get the result. Okay, so what this did was it took all the points. It found, if it takes a point, is it closer to that 3, 3, 3, 3? Is it closer to the -3, -3, -3, -3? Whichever way, it puts it over there. Then it takes another point. It decides which way to put it. Where is it closer to? And then it takes the next point. Where is it closer to? Where is it closer to? Until all the points are in a group. Then what it does is it calculates the center of all the data points. All right, so now we have a new set of 2 centers. All right, so next, it goes through that process all over again of seeing which center is it closer to. And it does this over and over and over until the points no longer move around. This is a very fast algorithm. This is a very good choice if you need to cluster large data. All right, so something about this is I'm setting it up so that I have 2 groups. I'm partitioning it into 2 data points. Why did I choose 2? Well, let's say that I did not know that I had 3 populations in here. If I didn't know that I had 3 populations, I look here and it's like I have a cloud, I have a cloud. I look here and it's like I have a cloud, 2 different clouds, 2 different clouds, 2 different clouds. So if I didn't know that there was a categorical variable associated with this, and I just looked at the data, I would think, oh, there's probably 2 different groups. So I chose 2. When it comes to the partitioning, if you don't know, go low. All right, so here are the new centers. And so here, I can look through here. So remember, I normalized my data, right? So with my normalized data, anything greater than 1 is greater than average. Anything less than 1 is less than average. Okay, so we can see that we have this group, we have greater length, lesser width, greater length, greater width, and then here we have lesser length, greater width, and lesser width. Okay, and then here we can see how the groupings actually fare out. So we can see that the first rows are going in the second group, that is this one. So we know that it was Setosa. Setosa tends to have lesser septal length, greater septal width, lesser petal length, and lesser petal width. And then the other two tend to have greater, lesser, greater, greater. All right. And so now something that can help us see if we have good clustering is we can check the ratio of between sum of squares and total sum of squares, similar to F statistic. And we can look at that, and we see that it's about 63%. Okay. And now, if I was to take the k-means object I have right here, and I want to look at individual components, this list tells us what are those individual components if I want to start digging in and start evaluating this a little bit more closely, which we'll do in later videos. All right, so now I want to visualize what's going on. All right, so one thing I just did was I did the pairs command and I plotted everything. Well, that's a way to visualize this also, but it gets hard to interpret all of those plots. If I look at this, I've got 1, 2, 3, 4, 5, 6, 12 different plots to interpret. That's a lot. I don't have a lot of brain power, so I can't do 12 plots. I mean, it's quite a bit. Now, you could say it's just 6 because of symmetry, but still, it's a lot to look at. It's a lot to interpret. What I want to do, I want to summarize this in a little bit easier manner. So what I'm going to do, I'm going to take principal component analysis. So if you don't know what principal component analysis, just nod your head, enjoy the video, take a sip of your coffee. And just kind of chill out with me for a moment. All right, so principal component analysis basically tries to represent the data in fewer dimensions. And so I'm going to take the first 2 dimensions, principal component 1, principal component 2, and I'm going to scatter plot along those 2 like subdimensions. And we're going to see what happens. So when I do that, I see that I have a cloud and I have a cloud of dots. And they're separated from each other. You see how there's kind of a gap here? Since there's a nice big gap, I believe that I have good clustering. All right, so now let's go ahead and plot the same scatter plot, but now I'm going to put species onto there. When I do that, I see that the Setosa group is very distinct from the others, and I can see that the other 2 species, they're in the same cloud, but I can see that there's kind of like a gradient along this direction. But my model, my clustering, does not detect it. Why didn't it detect it? Because I only have 2 clusters. And now I can visualize it by individual cluster, and this is pretty decent, honestly. I can see that every single time there is a gap between the red and the black clouds of dots. So I feel like I have a good clustering going on. Now, a shortcoming of this is because I know that this cloud has 2 different species, and these 2 species are clumped together. But if the purpose is to detect this species versus not this species, then this is a very good predictor variable. Well, that's all I've got for you. Take care and goodbye.